Hi. So in this video, we'll go a little bit in detail on the Deutsch-Jozsa algorithm and come up with analysis of it. So let's recall what the Deutsch-Jozsa algorithm is. So you have a function f from 0, 1 power n to 0, 1, and you're given the promise. So promise is function is either constant or balanced. So constant means that all the 2 to the power n inputs either all go to 0 or all go to 1. And balance means that half the inputs go to 0 and the remaining half go to 1. Now, the classical algorithm or the brute force classical algorithm that we can find is to um, make the distinction between whether the function is constant or balanced is requires so brute force algorithm requires 2 to the power n minus 1 plus 1 queries to the function to distinguish between these two possibilities, right? So and we know that the Deutsch-Jozsa quantum circuit requires just one run, so one query. So it seems that we have created a exponential gap between the quantum and classical case. However, that is not quite the case. So let me give you first a randomized algorithm that succeeds with probability 2 over 3. So randomized algorithm is an algorithm which has a random step, and then the algorithm uh, may give a success, but not always. So it may fail also. So in this case, we'll give a randomized algorithm. So let me give a randomized uh, algorithm. So this is a classical algorithm with some random steps that succeeds with probability 2 over 3, right? So here is the algorithm. So algorithm is the following. So select randomly. Randomly means uniformly at random. Two inputs. Choose two inputs I and j, and evaluate the function at that. So and evaluate f of I and f of j. So you have two calls to the function, and then if fi not equal to fj, then declare the function as balanced. As balanced. On the other hand, if fi is equal to fj, then toss a coin with the probability of heads is equal to 2 over 3. So um, toss this coin, and if head occurs, declare the function is constant. And if a tail occurs, declare function to be balanced. Okay, so this is an algorithm, and as you can see, there are some random steps that the algorithm takes. And I claim that this algorithm succeeds with probability 2 over 3. What does success mean? Success means that if the function is constant, then 2 out of 2 over 3 probability is the probability that this algorithm outputs that the function is constant. And if the function is balanced with probability 2 over 3, the algorithm outputs that the function is balanced. So let's prove that that is the case. So claim is this algorithm succeeds with probability 2 over 3. Okay, so there are two cases, right? Function is constant or function is balanced. So if let's first assume that the function is constant. So what is the probability that algorithm succeeds? So what is the probability that algorithm succeeds given function is constant? Okay. So what will this probability be? Well, if you look at the algorithm, we choose two inputs. Now, step number 2 cannot happen, right? I mean, fi cannot be not equal to fj if the function is constant. So the probability that the algorithm succeeds if the function is constant is just the probability of getting heads in step number 3. So this is equal to P of H, which is equal to 2 over 3. So if the algorithm succeeds with probability 2 over 3, if the function is constant, right? And let's look at the other case. So probability that algorithm succeeds given function is balanced. Okay, so how does that happen? Well, firstly, when we choose the random inputs I and j, the probability that fi is equal to fj is 1 over 2, and fi not equal to fj is also f over 2, is 1 over 2, right? So the two ways that this algorithm will succeed is if fi not equal to fj, right? And then you go into step number 2 and declare the function is balanced. So that probability is half. Or if fi equal to fj, and then in step number 3, a tail occurs, right? So those are the two possibilities, and they are mutually exclusive. So this is going to be equal to half. So this is the probability that our random inputs that we call fi is equal to fj, right? Since half the inputs go to 0 and the other half go to 1, so the possibility of our randomly chosen inputs are the same, right? The function is the same as those randomly chosen input is half, or it can be fi not equal to fj, and a tail occurs. Sorry, this should be not equal to, because we are checking the function to be balanced, right? So if this happens, or fi equal to fj and a tail occurs, right? So this will be half multiplied by 1 over 3. So this is equal to 1 over 2 plus 1 over 6, which is also equal to 2 over 3, right? So this will be the probability of success. Now, so we have devised an algorithm that succeeds with probability 2 over 3, no matter whether the function is constant or the function is balanced. Now, does that help us? What we can do is do a process which is called boosting or amplification. So boosting or amplification. And the idea is to run the algorithm repeatedly for, let's say, n times, and then do a majority vote and output the answer that has the majority of the outputs. And let's say you run the algorithm for n times and you get something like balanced, constant, balanced, and so on. And what you do is count the number of balances, count the number of constant outputs, and then output which has the larger value. So output the majority vote, right? So you have to rerun the algorithm n times. Now, we want to make sure that we don't add any more overheads by running the algorithm n times. And it turns out there is a inequality in probability, which is called Chernoff bound, which comes to the rescue. And so roughly the Chernoff bound says the following. Suppose you have a xi equal to 1 if ith run of the algorithm. So we have n iterations. So if ith run outputs correct answer, and 0 else, then if we look at um, summation xi, so let x be the random variable, which is summation xi I equal to 1 to n, then this counts the number of correct answers, right? So we want x to be greater than n over 2. And we want the probability of x less than n over 2 to be small. And so the Chernoff bound says the following, that suppose expectation of this x is equal to mu, then the probability of x less than 1 minus mu, 1 minus, sorry, delta times mu is less than or equal to e to the minus mu delta square over 2. So what this inequality or Chernoff bound says that if you have a random variable, and in this case our random variable is the summation of xi, and if you have the expectation mu, and if this is mu minus 1 minus delta, so mu into 1 minus delta, should be mu minus mu delta, right? And you have some random variable, that the probability that the random variable goes below in this region goes down exponentially fast. Okay, so which means that the probability that the random variable will be away from the mean goes down exponentially fast, right? Most of the probability is concentrated in and around the mean. Not only that, but the probability of going outside the mean in either direction is going exponentially fast. Because of that, we have that the probability of x less than n over 2, this will be the case if your majority vote doesn't give the correct answer, is less than gamma to the n, where gamma is a number between 1 and 0. And therefore, since it goes down exponentially fast like this, you don't need that many iterations to give you the correct answer. So the if you have you want to boost the probability from 2 over 3 to, let's say, 1 minus epsilon, where epsilon is very small, then you need to repeat the algorithm. N is of order log of 1 over epsilon times. Okay, so we run the algorithm, the original one that we devised over here, which is which gives success probability of 2 over 3, and then do this boosting by rerunning these algorithms n, not that many times. It is just order of log of 1 over epsilon, where 1 minus epsilon is your expected success probability. And then you get the correct answer with a very high likelihood.